Okay, this is ionization energies or ionization enthalpies. Now, when we're talking about this, you always need to remember three things. Okay, you need to remember distance from nucleus, the size of the charge in the nucleus, so how many protons do we have, and you need to remember electron shielding. Okay, now basically electron shielding is how many electrons are in between the electron being removed and the nucleus. For example, the electron here has got an electron shielding of 2 because there's 2 electrons between itself and the nucleus. Basically, all you need to do to calculate electron shielding is calculate how many electrons are in inner shells compared to the electron you're looking at. If I had beryllium, this has still got an electron shielding of 2 because this electron here is in the same space as this one, so it can't shield it. It's not in an inner shell. So in order to be electron shielding, you have to count the electrons in the inner shells. It doesn't count if it's the same shell as the electron being removed. Okay? I'm sure you know how to count the number of protons, and the distance from the nucleus we're going to go over now. Okay? So this is our period 2 going across. Lithium, beryllium, boron, carbon, nitrogen, oxygen and fluorine. Okay. Now as we go across a period, and I've used this as an example, you can look at any period in your periodic table. As you go across, the number of protons increases by 1. So the nuclear charge is going to increase by 1. Now, protons have a positive charge, electrons have a negative charge, so they're attracted to each other. Okay? I always think as the number of protons in a nucleus as the number of people on a tug of war. Okay? The electrons try and get away, but it's attached to a rope, and the number of protons is the number of people pulling the rope. Lithium has only got 3 protons, it's only got 3 people pulling on the rope. So how far do you think they can pull those electrons in? How close do you think they can get them? Not very far at all, because there's only 3 people. So lithium is actually fairly large. Okay? Its outer electron shell, and I haven't drawn the inner ones to save time, the outer electron shell is actually quite far away from it. If I look at beryllium, that's got 4 protons, so that's got 4 people pulling that rope, pulling the electrons closer. So that's going to be ever so slightly smaller. If I have boron, that's got 5 people, so it's going to be smaller still. Carbon's got 6 people, 6 protons, 6 positive charges attracted that electron. So it's going to be even smaller and smaller and smaller until fluorine is just incredibly small, because that's got 9 protons, 9 people, 9 positive charges pulling the electrons in. Basically, what it works out is as we go across the period, because we've got more nuclear attraction, more positive charge in the nucleus, the atomic radius, the size of the atom, gets smaller. Now, as the size of the atom gets smaller, it becomes harder to remove an electron because it feels more nuclear attraction. The closer an electron is to a nucleus, the stronger the nucleus can hold it. So, as we go across a period, the ionization energy increases. Okay, I'll say that again. As we go across a period, the ionization energy increases because there's more protons, meaning more nuclear attraction, meaning the atomic radius decreases because the electrons are pulled closer. Okay, that's across a period. You also have to know, or have to explain what happens as we go down a group. So I'll go for an example of that. So really, there's one reason why ionization energy increases across a period. When we go down a group, we need to give 2 reasons for this. Okay? So as an example, let's have fluorine and chlorine. So this is going down my halogens. Now fluorine has got 9 electrons. 2 in the first shell, 7 in the next shell. Chlorine has got 2 in its first shell, it's got 8 in the next shell, and then it's going to have 7 in its third shell. Okay, and if I was to go on to bromine further down, that would have an extra shell on top, and then iodine an even further shell, then astatine an even more shell. So basically, and this is the same for any group, as you go down a group, the outer electron, the one you're removing, is in a shell further out. Okay, a shell of a higher quantum number. This has two implications. One, if it's in a shell further out, then your atom's going to have a larger atomic radius, and it's going to be further away from the nucleus, and it's going to feel less nuclear attraction. So that's one reason why as you go down a group, the ionization energy decreases. So it's easier to remove an electron from chlorine than it is from fluorine, because the electron you're removing is further away from the nucleus. But that's only half the story. It's not just about atomic radius. With this, it's also about electron shielding. Let's have a look at that. How much electron shielding do we get in fluorine? Well, let's say it's this electron being removed. As these are in the same shell, they can't shield. As these are in an inner shell, they can. So fluorine has got an electron shielding of 2. But if I look at chlorine, it's got 1, 2, so let's say this one's being removed. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in fluorine, I've got 2 electrons blocking my nuclear charge, blocking the attraction from the nucleus. That's not very much. So it's still, this electron here is still going to feel that force from the nucleus and make it harder for it to be removed. With chlorine, it's got 10 electrons blocking it. You can imagine this is the electron and you're the proton, you're trying to pull it, and all these electrons are getting in the way and they're not letting you do it, they're blocking the attraction. So this is going to feel less of a nuclear attraction. Okay, so to sum up, 2 reasons are the electrons are going into an outer shell, a shell further out with a higher quantum number, so we've got a larger atomic radius further from the nucleus. Also, they have more electron shielding because there's more electrons in the inner shells, and that's ionization energy.